everyone. Welcome back to Measure Theoretic Probability. We have been talking about expectation or expected value, and we've covered sort of two cases. One, the expected value of a simple random variable, and two, the expected value of a general non-negative random variable. Today, we're going to finish that out and deal with what happens when your random variable has negative parts or is completely negative. But before going there, I just wanted to say a couple of things. A simple random variable is necessarily discrete, but not the other way around. In here, we've yet to talk about distributions and things with names that you might recognize, like an exponential distribution, a Poisson distribution, things like that. The Poisson distribution, as an example, or like a geometric distribution, these are discrete random variables, but they're not simple because they fail one thing about being a simple random variable, and that is that simple random variables can only take on a finite number of values. They are, however, both non-negative random variables, and so we have covered their expectation with our supremum definition, because what we did here after leaving the simple case was talk about anything non-negative, and that includes discrete random variables or not discrete random variables. So this might look a little weird to you at this point, because from your previous probability or maybe math stat course, you know that when you deal with continuous random variables, you have integrals usually for expectations. And even though I didn't have any concrete examples last time, I drew some kinds of examples to help us just look at step function approximations. And those random variables that I drew, x of omega, those functions of omega, all looked continuous. And yet there was no integral in sight. So today, I want to start talking about integration in measure theory. We're going to drop expectation for a while and come back around to that after we've completed our discussion about integrating with respect to a measure. But first, let's just finish up the final part of expectation so far, pre-integration. And that is, we have to deal with negative random variables or random variables that are negative in some regions. So for a general random variable x, what I'm about to do is probably something you've seen if you've had a lot of analysis. We're going to define the positive and negative parts of this random variable, which is a function. So you may have seen before positive and negative parts of a function like called f. We're calling ours x. X plus is going to be defined to be the maximum of x and 0, whereas x minus is going to be defined to be the negative of the minimum of x and 0. So I claim that these are both non-negative. Suppose this is our function x of omega, because again, to us, random variables are functions. We have a positive part of this function, which is going to be this part in green. So I'm just tracing across the function as long as the function is non-negative. But you see, like here, whenever the function dips into negative values, I'm just going to flatten it out and define x plus to be 0. So this is what you get when you go across this omega axis and pick out at each point the maximum of x and 0. Whereas, I'm going to ignore this negative for a moment, if you go across and you pick out the minimum of x and 0, you end up with this red part down here. And when you take the negative of that, that flips up here. So what I've drawn, this green curve is x plus, and this red curve is x minus as defined here with the negative. So both x plus and x minus are non-negative, but we can get x back easily by subtracting here. It's easy to see that you can get the original white curve back by taking the green curve minus the red curve. And again, both of these are non-negative. Now, expectation is a linear operator, so we can run the expectation through here, and we can get the expected value of x by taking the expected value of x plus minus the expected value of x minus, and both of these expectations are covered by our previous work for non-negative random variable expectations, so we now know how to compute an expected value for a general random variable. Whether or not you're actually going to do it this way is another thing, right? When you first take calculus and you learn about integrals, I think I've probably given this analogy before, but in case I haven't, when you first learn about integration in just like Calc 1 or 2, but not analysis, I'm talking about like freshman, sophomore level stuff, You learn about integrals as limits of sums. You start partitioning things, but you don't do integrals like that, do you? You do integrals now using rules of integration, like if it's x to the n, you get x to the n plus 1 over n plus 1. So what we've been doing so far is kind of like how you first learn about integration as limits with partitions, but in the end, probably not how you're going to compute expectations. By the way, as a sanity check here, these expectations aren't going to make any sense if x plus and x minus are not random variables. Are they random variables? I'm just going to look at one of these. The other one is going to be quite similar. The answer is, of course, yes, or I wouldn't have defined my expectation that way. So to prove this, if you need proving, if not, skip ahead another minute in this video. Note that the random variable that I'm going to define, y of omega, that's defined to be 0 for all omega, this is a random variable. It is a function from omega into r, and it's measurable because the inverse image of any Borel set containing 0 is going to be the full omega, which is in the sigma field in the original probability space. And the inverse image of any Borel set not containing 0 is going to be the empty set, which is also in the sigma field. So inverse images of all Borel sets are in the underlying sigma field, which is, here, I didn't write it, but we've got an omega, an f, and a p. So this is a valid random variable. Now, we showed back in lesson or video 19, I believe, that if x and y are random variables, then the set of all omega such that x of omega is greater than y of omega is in the underlying sigma field, curly f. This implies that the set of omega for which x of omega is greater than or equal to y of omega is also in F. Why is that? Because in this statement up here, there was nothing special about x or y, so write it the other way around. We do know from lesson 19 that the set of omegas for which y of omega is greater than x of omega, that's in F, and this set down here is the complement of that. So we do have that it is also an F because sigma fields are closed under complements. So let's try to bring this all together in order to show that x plus is in fact a random variable. We showed in lesson 20, I believe, that if x and y are random variables and if A is a set from our sigma field curly F, then if we define a new function z of omega to be x of omega whenever omega is in A and y of omega whenever omega is not in A, then z is a valid random variable. Okay, so altogether now, let's go back to x plus. X plus of omega is the maximum of x of omega and y of omega, where y of omega is 0. That's how it was defined. And this is defined to be x of omega whenever x of omega is greater than or equal to y of omega. And it's defined to be y of omega whenever x of omega is less than y of omega. And yes, this could be less than or equal to, but we could drop it. We sort of have a continuous definition here. Whenever x of omega equals y of omega, then the maximum is x of omega or y of omega. So I understand if you want to put a less than or equal to here, but then understand that you could drop that equal sign. And so rewriting these conditions over here as if omega is in the set of omegas for which x of omega is greater than or equal to y of omega, and similarly down here, we now have a random variable, a set A that is in F at A complement. And so this is exactly like the Z from the previous slide. So we do know that this is a valid random variable. And that's one way we could show that x plus is a valid random variable. And it's really easy to do something similar to deal with x minus. So I'll leave that to you. This is about all I want to say about expectations today, except for one thing I do have to fit in here. The expected value of x for a general x we define to be the expected value of the positive part minus the expected value of the negative part. I just wanted to point out that if the expected value of x plus happens to be infinite, but the expected value of x minus is finite, then this difference is infinite, and we would say that the expected value of x is infinity. Whereas if the expected value of x plus was finite and the expected value of x minus was infinite, then we have something finite minus infinity, and we would say the total expectation there is negative infinity. However, if you do have the case where both of these individual expectations are infinite, you never want to say infinity minus infinity is 0 because it's not representing maybe the same infinity. It just doesn't make sense to do that. So we say that the overall expectation does not exist. Okay, so we did expectations without any integrals. We will actually do that eventually. But now I want to take a break from expectations and talk only about integration with respect to a measure. So notation that I want to use here, we're going to define what is meant by the integral over A of f d mu, where mu is a measure. It could be a probability measure, in which case we might write dp. It could be Lebesgue measure, in which case we might write d lambda. But mu is our general measure. This is also written as the integral over A of f of x d mu of x, or the integral over A of f of x mu dx. So all three of these mean the exact same thing. They're notations for the same thing. Okay, so recall the usual beginning calculus definition of a Riemann integral, where you define integration through you take your x-axis and you take whatever region you're looking at and you partition it up, and you use that partition to define rectangles. And you are approximating area under a curve by taking the area of these rectangles and then taking a limit. Your partition gets finer and the rectangles get thinner. But what if we tried to do that measuring the area of the rectangles differently? Remember back in the very first video for this course, I drew some region and I said, how would you measure this? One way for that 2D region was to just compute its area, but then we started talking about different ways you might want to measure it. And if you apply that kind of thinking to a Riemann integral, you're going to get a more general kind of integral. And that's exactly what we're going to talk about right now. So I'm going to let n omega be a non-empty set of anything. Doesn't have to be numeric. This is just our usual omega. I'm going to let curly f be a sigma field or sigma algebra on omega, and I'm going to let mu be a measure on curly f, which could be a probability measure, but I'm going to keep it a little more general here. Recall that omega and curly f together are known as a measurable space. It's ready for a measure, and once you include that measure mu, the triple omega, curly f, and mu is known as a measure space, and if mu happens to be a probability measure, then it's known as a probability space. Now, suppose that f, mapping from omega into r, is a measurable function. F is a simple function if it has this sort of form, if there's a finite number of terms where you have some coefficients and some indicators. This is exactly a random variable. If mu is a probability measure, then this is a random variable, but I'm not assuming mu is a probability measure. As we know from our treatment of random variables, the simple function f is measurable if and only if all of these sets, capital A1 through capital AN, are in curly f. So if we have a simple and measurable function, we define the integral over omega of f with respect to the measure mu. So I'm going to write that this way, but you saw other ways to write this. We're going to define it as the sum as I goes from 1 to n of ai times mu of the capital AI. Let's draw a picture. We've got a simple function. Here's an example. In this picture, it appears that I have 3 levels for this function. So n is 3, and I've got coefficients little a1, little a2, and little a3. And then we've got our capital A1, capital A2, and capital A3 corresponding to the values down here that will map to little a1, little a2, and little a3. So a2 happens to be a union of 2 disjoint sets, just for fun. If I want to integrate this, then basically I want to find the area under these rectangles, and the y-axis is in the reals, if you will. So we're mapping from some omega, the x-axis doesn't even have to be numerical, and to the reals, so the y-axis is in the reals. So we're going to measure the height of these rectangles just with normal Lebesgue measure. The height of the first rectangle is a1, the height of the second and fourth rectangles is a2, and the height of the third rectangle is little a3. But we're going to measure the base of these rectangles through the general measure mu. So the base of this first rectangle is mu of capital A1, and the total base of the second and fourth rectangles is the mu measure of capital A2, etc. This is how we define this integral with respect to the measure mu. It looks just like what we did before in the simple case, but we're measuring the rectangles differently, And really, that just means we're measuring the base of the rectangles differently. We're measuring the height the same way we've always measured height. That's how I define the integral over the entire omega. Now, suppose I want to integrate over a set, some subset of omega. So here's my function again, and then I'm going to take this interval here to be a set B. It doesn't have to be closed, doesn't have to be an interval. It's just my example. In my particular picture, B does not intersect A1 at all. It intersects A2, but not all of A2. Intersects part of A3. So what I have here is in this picture, B is separated into two regions. I've got the part that intersects with A3 and the part that intersects with A2. And for simplicity, let's assume that in our simple representation for F, we do have disjoint sets and distinct coefficients. With this picture, we're ready to define the integral with respect to mu over a set B. We're going to define it as the sum, as I goes from 1 to n, of the little ai times the mu measure of ai intersected with B. So if you look in this picture, you're basically just computing the area under this curve, which is a step function, and the step function is 0 out here. So the pieces of area we have are in here and in here. And to measure those, we measure, in this case, A3 intersected with B and A2 intersected with B. And in this definition down here, A1 intersected with B is empty, and the mu measure of an empty set is always 0, so it's all good. So what we just did is known as Lebesgue integration. And you'll note that, or you should note, that Lebesgue integration does not necessarily use Lebesgue measure. If it does use Lebesgue measure, that means that we're measuring the bottoms of those rectangles with just normal, usual length. In this case, we essentially get the same thing as the Riemann integral. I say essentially because there are cases where the Riemann integral won't exist, but Lebesgue measure will. And maybe we can get into that another day. But, when you do a regular Riemann integral, you define a base, right? And then you have a function, and you have to define the height of your integral. Sometimes you use the left endpoint of that rectangle. Sometimes you use the right. Sometimes you use a midpoint. Sometimes you use the maximum value of the function in that integral. There's all sorts of things you can do. But if they don't give you the same thing, then the Riemann integral is not well defined and may not exist, whereas the Lebesgue measure the Lebesgue integral using Lebesgue measure would exist. So that's a little more than I wanted to say today, but I will come back to that. But the main difference is in one case, we partition the domain of the function, that's the Riemann integral, and in the other case, we partition the range of the function. That's, partitioning up on the y-axis there and using that to define the sets that you're integrating over. I know I said I wasn't going to come back to it, but we just talked about how if you have a simple f, say of this form, then the integral over omega with respect to the measure mu looks like this. So if you had a probability space and mu is actually p, then if you have a simple random variable, that's just f, right? That's just a simple function, but we usually call it capital X in a probability space. We know that the expected value of x is going to be the sum of whatever coefficients used to define the simple random variable times the probability measure of the events being indicated. And now we have new notation. Look at this and this and this. This is actually the integral over omega of x dp. The expected value of x is the integral over omega of x dp. Here we're integrating against a probability measure, and we know how to do that now in the simple random variable case. Let's get back to the general measure. So I have a measure space, and I have maybe a function f from omega into r that is measurable, but not necessarily simple. We're going to do just like we did in the expectation case and random variable case. We're going to talk about non-negative f first. So if f is greater than or equal to 0, we're going to define for any set A in the sigma field the integral of f over A against the mu measure. So d mu is going to be defined as a supremum of integrals over A of a function s d mu, where the s's are simple measurable functions we're looking at all non-negative simple measurable functions that are trapped between 0 and f for all, or even almost all, omega. This is exactly what we did when we were defining expectation for a more general non-simple random variable. We define the expected value of a random variable x to be the supremum of a bunch of expectations of simple random variables. If this d mu were dp in both cases, and x was, or this f was denoted by a capital X, and this s was a capital Y, this is exactly what we did in the expectation case. As for some terminology, if we have our measure space and we have a function f from omega into the positive reals that is measurable, so this is just what I had on the previous slide, but I said it differently. I said we were going into R, and then I said, by the way, f is greater than or equal to 0. So now I said that all at once. We've just defined the integral over omega of f d mu to be a supremum. If this supremum is finite, we say that f is integrable, or more specifically, integrable with respect to mu. And if the supremum is not finite, we either say that f is not integrable, or that f has infinite integral with respect to mu. Similarly, if we take a set A in curly f, so I just want to say sort of the same thing without the full omega. If the integral over A of f d mu is finite, we say that f is integrable over A. And if we know what measure we're working with, we don't have to add more to that, but it might be important to say with respect to the measure mu. We could have a case where our function f is integrable with respect to mu over a set A, but not over the whole space. As you can imagine, and I'm about to prove some facts for you, the integral over the whole space would be larger because we are talking about non-negative integrands. And so you can imagine the integral over the whole space being infinite, but not when you restrict to some subset A. So we might be integrable over A, but not integrable in the wider sense. So let's look at some of those facts. So suppose I have a measure space, an omega, a curly f, and a measure mu. Suppose I have a couple of non-negative measurable functions, f and g, and suppose I have a couple of sets, capital A and capital B from curly f. First fact I want to talk about is if 0 is less than or equal to f is less than or equal to g, then the integral over A of f d mu is less than or equal to the integral over A of g d mu. Super believable. Maybe you don't even want to see a proof. Don't worry, it's only going to be 2 lines. So how would we show this? If s is a simple function that is stuck between 0 and f, then s is between 0 and g. So the supremum that we use to define this integral over here of g over a, it's going to be a supremum of the integral over a of s d mu, where we're running over a lot of different s's. Any s that we have to run over to compute this integral, we have to run over to compute this integral, and this integral may involve a supremum over more things, and that can only be larger. You know, a supremum is like a maximum. You throw more things into that set, the maximum could stay the same or potentially be larger, and that's the result we wanted. As a second fun fact for today, suppose that our sets from f are capital A and capital B. Suppose that A is a subset of B. Then I claim that the integral of f d mu over A is less than or equal to the integral of f d mu over B. So to prove this, I'm going to take a simple s that is trapped between 0 and f. Now s has, being simple, has some form like this. I'm going to say the sum as I goes from 1 to n of little ai times the indicator of capital AI of omega. Now, if capital A, the set A, is contained in B, then AI intersected with A has to be contained in AI intersected with B for all I. Because of this containment, if we take the mu measure here, then by monotonicity of a measure, mu of this set is less than or equal to mu of this set. And we saw this back in lesson 3 for a general measure. So how are we going to define this integral here? We're going to take a supremum over S of integrals that look like this. Integral over A of S d mu. Because S is simple and has this form, if we're integrating over A, we've already talked about how that means that the integral is going to be, for this simple S, the sum as I goes from 1 to n of little ai times the mu measure of capital AI intersected with A. Now we just said that this term here is less than or equal to mu of AI intersected with B, so I'm going to write this inequality out. This whole thing is less than or equal to the sum as I goes from 1 to n of little ai times mu of capital AI intersected with b. And this is precisely how we define the integral of s d mu over b. And this is going to be less than or equal to the integral of f d mu over b, because this is defined as a supremum of terms like this. So using this whole line here, we see that the integral of f d mu over b is an upper bound for terms like this for any simple s between 0 and f. Now, the integral of f over a is defined to be a supremum of the integral over a of s d mu, right? And that supremum is taken over simple s that are trapped between 0 and f. And this is less than or equal to the integral over b of f d mu, because the supremum is the least upper bound for terms like this. And we just said that this is an upper bound for terms like this. So the least upper bound is going to be less than or equal to any given upper bound. And look, that's what we wanted to show. We wanted to go from here to here and get this inequality. So we're done. The third fun fact is for a constant c greater than or equal to 0, the integral over a of c times f d mu is equal to c times, you can pull c out of the integral. We don't actually need c to be non-negative, but we do for now because we've only defined integrals for non-negative functions. So if c was negative, we technically don't know how to define the integral on the left side here, even though I think you might have an idea about how that would work. So I'm going to leave this one for you as a couple of hints for proving this. The first thing I would do is say, look, this is clearly true when c equals 0. I get 0 equals 0. So I would say, okay, assume c is not 0, and that's where I would start the proof. And then I would note that this left side, the integral over a of c times f d mu, is defined to be the integral over a of s d mu, where we take a supremum over all s that are simple and trapped between 0 and c times f, right? Because this is our function for this integral. And so we want to look at simple s that are trapped between 0 and this function. And then go. I think it'll be pretty straightforward to get this result. We're ready for fun fact number 4. So if f of omega is 0 for all omega in some set A, then the integral of f with respect to mu over the set A is 0. Shocking, right? I know. I'm proving these things anyway because I think sometimes those are the hardest things to prove, the things that are so obvious. Like, of course, so let's try it. To prove this, I need to define this integral, so I'm going to take simple s, any simple s. I know this is going to be a hard video to watch because in the, I know in my videos, you can't tell the difference between me saying s, and f. But yeah, I don't know. It is what it is. So I'm going to take any simple s that is between 0 and f. And we want to show that the integral over a of s d mu is 0. If this would hold for all s that is simple and between 0 and f, then check this out. The integral over a of f d mu is defined to be the supremum of integrals that look like this with an s in there over a bunch of different s. But if all of these are 0, then the supremum, or least upper bound, is 0 as well, and we're done. We'll have that the integral of f d mu over a is 0. So it remains for us to show that for any simple s stuck between 0 and f, the integral over a of s d mu is 0. Let's do it. Note that our s is assumed to be between 0 and f, and because f is equal to 0 for every omega on a, then s of omega must also be 0 whenever omega is in A. Now, s being simple has some form, the sum as I goes from 1 to n of like little ai's times the indicators of the capital ai's of omega. So the integral over a of s d mu is the sum as I goes from 1 to n of little ai, and then times the mu measure of capital AI intersected with a. So let's look at these mu's. If we have, in the case that capital AI intersected with A is empty, then the mu measure is 0. I want to show that this whole thing is 0. and we'll get zeros in those cases. Now, in the case where capital AI intersected with A is non-empty, what is the mu measure then? It actually still could be 0. We've talked about sets that have probability measure 0, even if they weren't empty. So just being not empty does not mean that the mu measure is non-zero, but we're not sure. But it would be okay if that coefficient was forced to be 0, and that's going to be what happens. So let's look at a picture. Here is just an example of an F, and you can see it's 0 in some places, and I'm going to define a set A, and the set A has to be always in places where F is 0. So maybe A consists of these two disjoint intervals here. I shouldn't say disjoint because this is just an illustration. Again, omega may not even be numeric and not be something you can look at on a line like this, but hopefully you get the idea. Now, let's look at any simple function that's under F. So I'm just going to draw something, not something that's necessarily approaching F or being increasing or decreasing or anything like that. If it's under F, then S definitely has to be 0 whenever F is 0. But S could also be 0 even if F is not 0. So you can see like here, it's maybe a little hard to see, but I've drawn S to be the whole line from here to here. So we definitely have it 0 when F is 0, but it may be 0 otherwise. So if capital AI intersected with capital A is non-empty, then I claim that S of omega must be 0 on AI. The way I drew this S, maybe this, and this look like they're at the same height. So the corresponding omegas, maybe we'll call all of that capital A1. And this, and this look like they're at the same height. So I'll call the corresponding omegas capital A2. And the next kind of heights I have here are the 0 heights here and here. And maybe I'll call this capital A3. So it appears, if I were to use that notation, that capital A3 intersected with A is non-empty. But necessarily, on capital A3, the only way you could have that non-empty intersection is if little a3 is 0. So I hope that makes sense. Going back to this case here, if capital AI intersected with capital A is not empty, we are forced to have the coefficient little ai be 0. So between these two cases, this sum, all of the terms of this sum are 0, so the sum is 0. So the integral over A with respect to mu of S is 0, and that's what we needed to show. We talked about earlier how that would give us the result we want, that the integral of F with respect to mu over A would then have to be 0. So I think I'm going to cut it there. I have a few more fun facts for you, but I'll start the next video off with them, and then we'll talk about integrating more with respect to a measure, and in particular, Lebesgue's monotone convergence theorem. A lot of things we did today with integration looked just like things we've already done with expectation, and I think Lebesgue's monotone convergence theorem is going to look that way as well. It's about an increasing sequence of functions converging to a function, and can you put the integrals through that limit as well? This looks just like what we did with expectations, but have we completely proven it? Have we relied on something that was true for a probability measure only? You're going to have to come back to find out. I hope to see you in the next one.